Hey everybody, we're going to start today and talk about the inverse function theorem. It's one of the last topics when we start talking about derivatives. So, the inverse function theorem, there are basically three things that we want to cover about it. First of all is we want to be able to use the inverse function theorem to find a derivative of a function's inverse at a point. We want to be able to use the inverse function theorem to find the derivative of a function as a function of x. Okay, so the derivative of the inverse of a function as a function of x. And 2 and 3 kind of go together, because most of the functions we're going to be interested in are finding the derivatives of things like ln of x and trigonometric inverses. Okay, so let's go for it. Okay, so we start off with a problem. And here's the problem. F of x equals x cubed minus 4x squared plus 7x minus 1. Now it is 1-to-1, which means it has an inverse. The inverse is a function. However, solving this explicitly for f prime, for f inverse of x, is going to be a little tough. So if I want to try to find the derivative of the inverse, it's going to be pretty tough if I try to solve this for x. Okay, isolating x by itself is going to be a challenge. We can do it, I'm sure, but it's not going to be much fun. So we're going to try to find another way to do it. Okay, there must be a better way, and in this case there is a better way than solving explicitly for x and then finding the derivative. Okay, so here's what we're going to use. The inverse function theorem. Here's what it says. Let f be a continuously differentiable 1-to-1 function on the interval a to b. Then, f inverse of x is also continuously differentiable on the interval either f of a to f of b or f of b to f of a, depending on if it's an increasing function or decreasing function. And its derivative is given by this. The inverse's derivative of x, that's what this says here, is equal to 1 over the derivative of the original function with the inverse function evaluated at x plugged in. Okay? So it looks a little strange, but we're going to first of all justify it kind of geometrically, and then we will go ahead and prove it. Here we go. Here's the justification. Here's a picture. Over here, let me get my highlighter. Over here I have f, and over here I have f prime. Now notice that f inverse. F and f inverse are just inverses, which means that the x coordinates and the y coordinates have been flipped. This is the point AB, this is the point BA. Okay? So if I look at the slope of f at a point, which is the derivative, the slope, right? There's the run, there's the rise. Okay, it's going to be given by delta y over delta of x. Which means that since x's and y's are just switched for f prime, for f inverse, the derivative of f inverse will be delta x over delta y, right? Just the reciprocal, okay? And we're evaluating it at the opposite point. Okay, so here's what it looks like. The derivative of f prime, the derivative of f prime of a can be thought of in a certain sense as delta y over delta x. And again, that's what I just said. The derivative of f inverse evaluated now at b, because we've switched the coordinates, right, is going to be at delta x over delta y. So everything gets switched. A becomes b, delta x becomes delta y, and so on. All right. So notice that f of a is b. Okay, that's what this means. F of a is b. Okay. So f inverse of b is equal to a. Is that all right? Okay. Just because it's a 1-to-1 function. So notice here, all I've done here is substitute. B is f inverse of, sorry, not b. Sorry, this is not a direct substitution. I've done it from here. F prime of a, where a is equal to f inverse of b, right? That goes in here, and I get this. F inverse of b plugged inside of f prime of a is delta y over delta x, right? That's what I have. Basically, I've taken this and combined those two statements. Okay, that's equal to delta y over delta x. But notice that delta y over delta x is the reciprocal of this, right? So these two here are reciprocals, which means that delta y over delta x is a reciprocal of this statement right here, or 1 over that statement. So that's kind of the argument. Basically, don't worry about the particulars in terms of how we've done it. But if we think about f and f inverse, in some sense their derivatives must be reciprocals. Okay, and that's kind of the intuition I want you to have. Okay, so let's look at a problem now. This is similar to the problem I put up, except that I've changed the input here to -1 to make things work out. What we're looking for is we're looking for the inverse function's derivative evaluated at -1. I had it at +1, and -1 makes this work a lot nicer. Okay. So here's what we're going to do. We're looking at f inverse prime of -1, which is equal to, and this is just by the inverse function theorem, 1 over f prime of f inverse of -1. Okay, so we got to find f inverse of -1. So what that means is that it's the same as saying that f of x equals -1. So I have to solve for x in this equation then. Alright, but again, the reason I made this a -1 is to make this work out quite nicely for us. Let's take a look at this. What value of x will make the output be -1? What's nice about this is the number ends up being something very simple, ends up being 0. Right? And since this is 1 to 1, we know there's only one value that's going to work there. Okay, so we plug in at x equals 0 and I get y equals -1. So the inverse, if I put in -1 into the inverse, I should get back 0. That's what an inverse means. A couple stray marks there. Okay. So f inverse of -1 is 0. I did this without ever actually knowing what f is equal to, what f inverse is equal to. I used some knowledge. Maybe I could use some technology to do this, but basically I used some knowledge to find the value at a function without actually knowing the inverse function itself. Now here is a restatement of the theorem we had before, right? This is the theorem before, except now we know that f inverse of -1 is equal to 0. F inverse of -1 is equal to 0. Oh, that's not what I want. It's equal to 0. That goes there. It went there. So now I have that f inverse prime of -1 is equal to 1 over f prime of 0. Okay, but that's not so hard to do. Here's f prime. That's pretty easy. Finding the derivative of the original function wasn't so bad. That's 3x squared minus 8x plus 7. So all I have to do is plug a 0 into that, and I can figure out that the derivative of the inverse function of f evaluated at -1 is 1/7. Okay. All right, so that's an example of how we use it to evaluate the derivative of an inverse function at a point. But we can use it even more powerfully to discover derivatives of other functions. So far we've learned what the derivative of e to the x is. And I'm going to spend a little bit of time here and justify what the derivative of a couple other related functions are. So we're going to end up today with all the functions you could ever want to find derivatives of. So we're going to find the derivative of ln of x, and we're going to use the inverse function theorem to do it. So ln of x equals y. That's our function we're finding the derivative of. Now, I can state ln of x as the inverse of e, right? Remember that ln of x is often defined this way. ln of x is defined as the inverse function of e. Okay. If ln of x equals y, then e to the y equals x. That's a definition. Okay. So let's take a look at this. Okay. How did I get this? Okay. Well, the inverse function theorem says the derivative. I think of ln of x as an inverse of e. So to find the derivative of the inverse evaluated at x, that's what we have on the left. I'm going to take 1 over the original function, which was e, with the derivative of the inverse function. Okay, so e is the inverse of ln of x. The derivative of e is itself e. That's where this comes from. That's f prime, and I put in f inverse back into it. But if we look at this, this is nothing more than x in the denominator. So another derivative you need to know, frontwards and backwards, is the derivative of ln of x is 1 over x. Okay, so we're going to take that. I want to add in one little thing. It's not exactly part of the inverse function theorem, but it's going to round out our derivatives of exponential functions. And that is, what about the derivative of a exponential function not of base e but an arbitrary base? So it could be 2 to the x, it could be 8 to the x, could be anything to the x power. Now the power rule does not work here, because remember the power rule says x is in the base. Now I have x in the exponent. Okay, so we get a little tricky here, and we rewrite. Since I know the derivative of ln and I know the derivative of e, I rewrite it. Okay, this is the same as saying e to the ln of a. That is equal to a itself because e and ln undo each other. So I rewrite it as e to the ln of a. So it's just trickery. And I notice that now something raised to an exponent raised to an exponent, the exponents are just multiplied. So I can rewrite that as e to the x ln of a. All right. But now I know the derivative of e. Okay. I can just chain rule this sucker. Okay. It's going to be the derivative of e with the original thing inside times the derivative of what's inside. But notice the derivative of x ln a is just ln a because ln of a is just a number. Okay. So x times a number, the derivative of that is just the number. So the derivative ends up being e to the x ln of a times ln of a. What does that mean? E to the x ln of a, well, again, by the same logic, this is what I had right here, which is what I had right here, which is what I had right here. So again, if I work backwards, I can look and see that, oh, e to the x ln of a is actually just a to the x. So another one of your derivatives you need to have somewhere up in your noggin is that the derivative of a number to x, okay, is that same number to x times the natural log of that number. Okay? The derivative of a to the x is equal to a to the x times ln of a. Finally, we're going to talk about the derivative of inverse trigonometric functions. Now, these come up less often than others, but you do need to have a couple of these memorized, and they're some of the trickier ones we're going to come up with. Okay, so just as to recall, a trigonometric function, the inverse function, returns an angle, right? So you put in a ratio, you get out an angle. Most trig functions, you put in an angle and you get out a ratio. Okay, so we're going to try to find how the inverse function works. And we're just going to use the inverse function theorem. Here's what the inverse function theorem says. The derivative of the inverse of sine of x is equal to 1 over the derivative of the inverse, the derivative of f, so this is f inverse. So 1 over the derivative of sine, which is cosine, with the inverse function plugged in, with sine of the inverse function of sine plugged in. Now that was not well spoken. If I'm trying to find the derivative of the inverse of sine, I take 1 over the derivative of sine with inverse sine plugged in. There it is. All right, so how do we figure this out? This seems a little bit crazy, right? Well, this is just a statement of the inverse function theorem, so that's pretty straightforward. To figure out what the denominator here is equal to, we do a little bit of work, and it's kind of tricky, and it's a trick you're going to want to have up here. We're going to draw a right triangle. Okay. Now, like I said, this is an angle. We'll call it theta for now. Okay. This is a ratio. Okay. Now remember SOHCAHTOA. Sine is opposite of our hypotenuse. This is a ratio. X is a ratio. So x over 1 is a ratio. So from the perspective of this angle, okay, the ratio is x opposite over 1 hypotenuse. Okay, it's a right triangle. So theta, inverse sine of x is theta. Okay, we think of inverse sine of x as an angle. And the ratio associated with that angle here we're stating here is opposite over hypotenuse x over 1. So this is the right triangle that's being created. Here's our variable. Here is our hypotenuse. Okay, that's what this is saying. This statement here is describing this right triangle relationship. Okay, so what we need to do now, here's the angle that we're describing. I could actually write inverse sine of x right here in place of the theta. We need to take the cosine of that theta now, of that inverse sine of x. Okay, so cosine, remember, is adjacent over hypotenuse. Right? Adjacent over hypotenuse. So we need to figure out what this bottom length is equal to. Okay, well actually, we know this is a right triangle, so we can actually solve if we know this is length 1 and this is length x, and we know that this thing squared, we can call it a if we want. Okay, a squared plus x squared must equal 1 squared. Okay, well, if that's the case, can we solve for a? Sure. A is going to be equal to the square root of 1 minus x squared, right? Because a squared plus x squared equals 1 squared. Solving for a, I move the x to the other side, the x squared to the other side, and I square root both sides, and I get square root of 1 minus x squared. And we're going to keep this positive in this instance because we're just looking at an arbitrary right triangle. Okay, so the cosine of this angle, this right triangle relationship, is this side, square root of 1 minus x squared over 1. So this denominator ends up being right here. So the derivative of the inverse sine of x is equal to 1 over the square root of 1 minus x squared. Okay, so we're going to spend a little time with this one. Finding the derivative of inverse cosine is the same thing. We're going to draw a triangle in the same way, except that we're going to end up with beginning with x over 1 here. And then we'll spend some time thinking about what is the derivative of inverse tangent in class. Okay, inverse tangent is a little bit different, but it's actually it's based on the same principle. We're just going to build the triangle slightly differently based on what tangent is. All right, that's it for today. Thanks, guys.